Where's the whip for the ones who go overtime?
I like to motivate with a carrot rather than the stick. But anyways, so our first speaker today is Avishai Dekel, and he's going to talk to us about a mass threshold for gas disks and compaction-driven rings.
Thanks, Joanna. I don't think you meant me as one of the strong characters. I'm going to give you a theory talk today, and after my talk, it will be very nice to discuss how it may or may not agree with observations. So I'm going to tell you about a mass threshold for disk formation, and in particular about a mechanism to drive rings around galaxies after compaction. So the question I'm going to ask is, in this plane of mass versus redshift, where do we expect disks? At high redshift, at high mass, low mass, at low redshift? So my motivation, well, I'll give you two main topics that relates to this disk formation. The first one is going to be how mergers drive spin flips, which in an orbital time may destroy any disks that try to form. And my motivation here is, looking at this cosmic web gas evolution along streams, you notice how high sigma peaks merge. These are the nodes of the cosmic webs. And when they merge, the pattern of streams that feed each galaxy changes. And since the streams carry with them the angular momentum that makes the galaxy angular momentum in size, a major merger of high sigma peaks is going to cause flips in the spin and destroy the disk that was there. So my first guess was, let's do a very simple calculation based on halos, on dark matter halos. The merging timescale at high redshift, above redshift 1, scales like 1 plus e to the minus 5 halves. And this can be derived in a very simple analytic way and has been seen in simulations. The mergers as a fixed fraction of the accretion rate. The orbital time typically scales like the Hubble time, given that the radius of a galaxy is typically a fixed fraction of the real radius. So it goes like 1 plus e to the minus 3 halves above redshift 1. If you divide those two, you end up with a merger time to orbital time scaling like 1 plus e to the minus 1, and a normalization of about 1 is where z is 3. It means that above some redshift, maybe redshift 3 or so, these are disrupted by mergers in every orbit. They cannot survive, whereas at later times, the mergers are less frequent than an orbital time, and you can stick with a stable looking disk. So this is our naive expectation. It's based again on dark matter halos. But this is wrong. If you do it right, you really want to do the 1 over the specific accretion rate of baryonic material, not halos. And as you know, the baryons, the mass of the baryons is not exactly the mass of the halo. So you can break this ratio into 3 factors, assuming the baryonic fraction is constant. Now, for this one, I already told you we know the scaling. It's 1 plus z to the minus 5 halves. For this one, we know roughly the scaling. It's mv to some power of order unity. And for this one, if you take the scaling relations at redshift 1 to 3 in the Taccone et al. Paper, and Jonathan Froenig helped me get this specific ratio, m baryon over m star, it actually scales roughly like 1 plus z. Again, very crudely. I'm just trying to estimate what's going on. So you put all this together, and you get a merger time or a flipping time, which is proportional to 1 plus e to the minus 3 halves, not 5 halves. And there is an MV dependence right there, which makes a difference. So those two things make a difference to what you assumed from just the halos. And when you put this together with the orbital time and take the ratio, you end up with the flipping time over orbital time being proportional to the virial mass. I mean, this dependence of redshift and this one balance each other and take the redshift dependence completely away, and this introduces a new dependence on MVR. So instead of a cutoff in redshift, you expect a threshold in mass to be the dominant distinguisher between a disk and a no disk. And the critical mass is on the order of a few times 10 to the 11th solar mass. And you expect this disruption below this just because there are two frequent major mergers that cause flips in the orientation of the streams filling the galaxy and the angular momentum. It turns out to be true in the simulation. What I'm trying to do here is build up theory to explain what we see in the simulations, okay? So I really live in a simulation world. So this is two measures of diskiness, either a kinematic measure or a shape measure in the Vela simulations, like 30 or so simulations. And as you see, in the same plane we were talking about, the color tell you what is the average diskiness in each pixel in terms of either this or this parameter. Same story in the right and in the left, just to show you it's not specific to how we define diskiness. There's a clear gradient in the vertical direction. There's a clear gradient in the vertical direction going from red, non-disks, to disks, and there's barely any dependence on redshift at all. Again, the critical mass here is around 2 times 10 to the 11 solar mass for the halo, which is slightly below 10 to the 9 solar mass for stars, so it's small galaxy threshold. And there's no significant redshift dependence here at all. Maybe a little bit, I'll talk to you maybe at the end about this. So this is the main result from the simulation, and you saw where it's coming from my little analytic derivation. Watch the sky here, and this is the spin direction in every time step in this specific simulation, where you see the gas edge on and face on and edge on. You see big flips at the early times when the galaxy is below 10 to the 11 solar mass. At this point, okay, there's going to be a compaction event at a few times 10 to the 11 right here, and from then on, no more spin flips. The spin sticks to one direction in the sky and remains the same direction. It's a stable disk, and you can see it in the pictures. You can tell very well which is the plane and where is the spin direction. And this thing happens in almost every galaxy in our simulation. Many flips at early times when the galaxy is below a few times 10 to the 11, and no flips later on. Let me show you 5 examples showing the same thing. You see the big flips every 100 or so million years, which is roughly the orbital time, 100 to 200 million years. And then this marks the crossing of the critical mass, and then nothing much happens later. It sticks to the same direction in every galaxy. So this flip story is true in the simulation. In fact, if I use in the same diagram, now plot the cosine of the angle between successive time steps. So blue is no flips, yellow and red is big flips. You see the same story here. The diskiness is really correlated with a lot of flips in orbital time versus no flips in orbital time. So this is a real story, and this is the main reason for why this is destroying this down there, but not the only reason. You can see perhaps this is the line of 2 sigma peaks by Press-Schechter. You notice that the flips tend to happen when this is high sigma peaks. It's really mergers of high sigma peaks. Whereas the disk can be stable when the mergers are of lower sigma peaks, really mergers going along the same filament, and then the flip is not obvious in a merger. It can come in with counter-rotating orbit. So this is 6 different examples of galaxies below the critical mass. The gas is very amorphous. Sometimes compaction is coming, but a lot of mergers going on just before you reach the critical mass. Here you can see that at very high redshift, redshift 7 and on, you already have a nice disk because the galaxy is above the critical mass, even though it's redshift 7, where my initial guess was saying no way to form disks. Very nice disk formed by this high angular momentum feeding by those streams, 3 streams, and ending up with a clumpy, nice disk like people observe at high redshift. So this is my first chapter, and my second chapter is another reason why you get a stable, nice disk or extended ring above the threshold mass, and this has to do with wet compaction, which you heard about a few times, in particular in Sharon Lapin's talk today. So this is the cartoon showing what happens in time that causes compaction. The gas suddenly, in the inner 1 kpc, becomes much denser, and then it's depleted by star formation and feedback, and you end up with a blue nugget right there, and quenching no more star growth after that, and a crossing of dominance between dark matter and baryons around there. So this is the story of major compaction. It turns out that major compaction do not happen earlier because supernova feedback is very efficient, and it can halt the gas tendency to compactify in a merger or counter-rotating streams. But in this mass scale, where this happens, a halo of 10 to the 11.5 or so solar mass, supernova feedback stops being effective because the potential well is too deep. And that's where the gas can freely compactify when pushed in by, say, a merger. So we recover, if we plot sigma 1 in stars versus specific star formation rate. These are 8 galaxies, and you see this elbow or L-shaped orbit where you compactify, and then you quench from the blue nugget phase, and you have this peak here. And this is really very similar to what happened when you stack together different redshifts in a proper way, and you see the same thing observationally. In a study that I think Mark Reuter's company will discuss tomorrow, we use machine learning to find if there is a typical mass for compaction, the way I argued because of supernova feedback and hot CGM from the other side. So we saw this in a simulation very clearly, and Sharon showed you a figure. This is in candles, where we apply machine learning to learn the simulations and to see what is a blue nugget in the simulations, and then find the blue nugget in candles. And lo and behold, it favors this critical mass. And again, theoretically, we blame supernova feedback to suppress the blue nuggets at lower masses, and the hot CGM plus AGN feedback can suppress the feeding of cold gas for blue nuggets at much more massive. Not always, because there are streams, but in some cases, that's why you get this typical mass. Now here's a movie, a static movie. And you can start from here at redshift 4, and you end up at redshift 1. It's only the gas face on. You see, first 2 slides are really a compaction phase, and going into a compact blue nugget right there. But see what happens after the compaction, and that's what I want to point out. You start, immediately after the compaction, you start building a nice spiral arm disk around it, and it grows, and it grows, and slowly you can notice that there is depletion of the gas from the middle. And if you wait long enough, the middle becomes really almost empty, and a ring is forming, and is maintained, and maintained, and maintained, and maintained for about 8 gigayears in this case. A very stable extended disk that's really stable here, and clumpy. So I'm trying to explain this. This is just showing you that there's a big bulge growing during the compaction in this time. And this is the key here. These are just showing you 5 galaxies with rings to show it's a robust feature. And this is just to illustrate that this thing happened in the real universe. This is by Genzel et al. Showing rings. There are bulges in those cases. And he will tell us today that in some cases you get rings without bulges. So this is not a necessary condition, but maybe a sufficient one. And these are rings in low redshift. So I want to tell you why this happens. First, look at the kinematics. This is the rotation velocity as a function of time compared to the blue nugget time. And this is a dispersion. They're all divided by the instantaneous real velocity, just to be able to put all the galaxies together. You see, the point is that while sigma doesn't vary very much, it's mostly the rotation that changes. You have a transition at the critical mass or at the blue nugget from a dispersion dominated system to a highly rotating system. Angular momentum before the compaction is lost. Everything shrinks to the middle. After the compaction, angular momentum is conserved, and you can keep a large disk. So this is my theory. First, an old theory is that if you have an unstable disk, you have transport of angular momentum out and mass inflow and clamp migration inwards because of the torques by the perturbations of the violently unstable disk. And in this paper, we derived a formula, and I want you to focus on this parameter, which will be with us for the rest. It's the fraction of cold mass in the disk. It's the gas fraction plus the star from the recent stars that are cold and participate in the instability over the total, which includes also the dark matter and the bulge and the stellar mass. This ratio is smaller than 1, can be as small as 0.5. In these cases, 0.3, it can be 0.1 in what I'm going to tell you. So the inflow time was quite fast. But in 2 orbits, clumps were migrating inwards in those cases. But not in our case. So now I'm going to calculate the gravitational torque by the spiral arms inside and out on the outer disk, on the ring. My control of the remote is very poor. In the tightly wound approximation, in the thin disk, and I'm really based it on brilliant remain plus a little addition, but all the big calculation is there. It turns out that these are the results. The pitch angle of the spiral arms is going to be about 4 times this parameter squared, which is a number much smaller than 1 if delta t is less than 1. This is why you get a ring. Very small pitch angle and a ring. If you compute the change of angular momentum in this ring compared to its own angular momentum in 1 orbital time, it is proportional to this angle squared and proportional to another power of delta d and the amplitude of those spirals compared to the average disk surface density. You can translate this to an inflow time. How many orbits? It's going to be delta t to the minus cube orbits, a big number. It can be hundreds of orbits before this ring shrinks to the middle because of torques by the spiral distribution. I assumed here some typical number for the amplitude. So the precompacting ring does not shrink because there are inch streams that build the ring with angular momentum. Gas depletion and bulge formation generate high Q here because there is no gas, and also there's a big kappa in the Q parameter, so nothing forms here, there are no rings here, nothing to generate torques on the outer disk. And then the massive bulge makes this small, and you end up with a very slow time for migration inwards. That's the key. So Why do the rings survive? Let's look at some time scales. The orbital time we talked about, the accretion time we talked about, and these are the numbers put in, the inflow time we just computed, and the star formation rate using 1/2 of the depletion time is few orbital time. What you learn from this is that the accretion time is shorter than the inflow time, so the ring always accumulates by the incoming streams before it manages to flow in. And then the star formation rate is very short. This is an argument that we also had in Dekel and Burkhardt a few years ago. The dissipative inflow is impossible, okay? Because stars form before there is time to flow in. So at the same time, the Q parameter is really given by delta t to the -1. You can have a combination where you have a Q less than 1. The ring is unstable for fragmentation, but not for migration. You can have ring with no bulge if the dark matter help you get delta D small. You don't have to have a bulge. You can have a nice big dark matter dominant center and an extended ring in this situation. So I'll skip this part because Joanna is a strong character. and I want to tell you that now there's a flipping scale, there's a blue nugget scale, but there's also a supernova scale that below which supernova is effective. And these are black non-disk red disks, and we don't know which one is really the one responsible. I want to show you one figure where we plot diskiness as a function of time compared to the last flip, time compared to the last merger, or blue nugget. And it seems that this is the tightest one, maybe indicated that the story about blue nugget driving ring is the main mechanism that stabilizes disk and ring above the mass scale. So here's my conclusion. Am I getting the... No hope.
Unfortunately not.
So I'll take another 2 minutes then. I told you she's a strong character. External gas disks form above the threshold mass of a few 10 to the 11 at all redshift. Below this mass, there are spin flips which destroy it in orbital times. Angular momentum loss by torques from violent disk instability. Also, what I didn't mention, a prolate bulge in those low masses. They all make fast inflow and shrinkage of any external disk that tries to form. Supernova feedback perturbs this in many ways, especially in mergers. They cause starburst, which can blow out the disk, also holds infall of high angular momentum gas and prevent high angular momentum. A Varvemcrete, you do have external ring, which survives because of post-compaction massive bulge and or massive halo, which weakens the torque exerted by the spiral structure on a newly formed high angular momentum disk. And this is a new formula which you can take and try to recover. Not trivial, by the way, but simple result. And then infrequent flips and ineffective star formation, ineffective supernova feedback guarantee that there is no much perturbations to these disks that form and stable. And this is my last key point. Supernova feedback may be behind many of these things because it's responsible for confining the compaction to the critical mass around it. And then this leads to massive bulge, prolated to oblate transition, quenching inside out, and the formation of these bulge-supported rings. Thank you.
So one quick question, Nir?
For your spin flips, you mentioned primarily the mergers. Do you see in the simulations just smooth accretion, but some flip in a large-scale stream plane like the Danovich et al. Picture? Does that induce spin flips?
Well, we didn't look for it, but my thinking was in the first slide that if you are a node fed by 3 streams, They're not going to be big flips until the whole environment changes, then until you meet another node and the whole stream. But this is my speculation. Omri, do you have a better answer to this?
All right, thank you, Avishai.